Hi there. Okay, this video is on the subject of total internal reflection, and this only occurs when you're going from an object that's, from a medium that's more dense to a medium that is less dense. So I'd like to use a swimming pool as our example, although this can occur in all kinds of ways. So let's go ahead and start off with a surface of a swimming pool and a ray of light that's leaving the swimming pool. We want to observe what happens to our ray of light as it leaves the swimming pool at different angles. So let's shut down the line feature here and use our ruler so we'll know what angles we're dealing with. And again, we should go ahead and draw our normal. Where do we expect this refraction to occur? It's supposed to occur about right there, right? Okay. We're going to shine light in all different directions. So we start off with, you may notice that if we shine light directly out of the surface, so I'm going to start off with a red ray, and then we're going to gradually change these rays. So our red ray will go exactly along the surface. I'm going to scoot this over so that it's kind of clear what happens when you put a red ray out of the surface without interfering with our dotted normal here. Snell's law dictates that this ray, if it's coming in at an angle of 0 degrees with their normal, it should also leave with an angle of 0 degrees with the normal. When we put our next ray in, we can keep with the red ray, but this time let's go at an angle of, let's say, 10 degrees, and then let's calculate what the angle should be out of the water. 80. There we go. So we're going to come in with an angle of 10 degrees with respect to the normal, 80 degrees with respect to the horizontal. And then if we run our calculations with the index of refraction of water at 1.33 and the index of refraction of air at 1, we get 13.4 degrees, so not a significant deviation. Now what I want you to do is get your calculator. You can pause the video and get your calculator and ensure that you're following along with me on this. I need to be 90 degrees from the normal and then 13.4 degrees from that, which carries me down to about there. So that is the deviation we would expect coming out of the water at such a shallow angle. Okay, now shallow with respect to the normal, not with respect to the surface of the water. Make sure that you run that through your calculator. Again, we have that the index of refraction for water is 1.33, the index of refraction for air is 1.00, and we came in at an angle of 10 degrees, so we're going to measure this as 10 degrees, 20 degrees, 30 degrees, 40 degrees, and then 50 degrees, and see what happens. Okay. So that's our 10 degrees. As a matter of fact, let me go back and label these according to color. So I'm going to try with an orange ray. I'm going to do 20 degrees with respect to the normal coming out of the water, or approaching the surface of the water. And then I can do a green ray at 30 degrees, and then I can do a purple ray at 40 degrees, and then I will do a final ray that is deep purple for 50 degrees. Okay, so let's do our 20 degree ray now. Our 20 degree ray at orange, we need our ruler. We're going to go to 20 degrees from the surface. Go ahead and calculate this again. You're going to be using the sine of 20 degrees as your incident or incoming ray, and then your refracted ray is going to be given is the angle that you're solving for with the index of refraction of 1 outside, I get 27.1 degrees. So I'm going to take this to the complementary of 27 degrees is 63 degrees. So that one is going to be refracted like this. Okay. So let me go ahead and write this out as this goes to 13 degrees, and then our next one goes to 27 degrees. I'm keeping these in integers because I don't have any. It's fine. We're just rounding here. Our next one will be the green light. Let's take that one to be at an angle over here coming in, an angle of, let's see, we would want that to be 60 degrees because we want 30 degrees from the normal. So I'm going to draw this one here. And if it's helpful, we can also, when we draw that ray, we can begin drawing our angles here as well, so that it's a little clearer what we're doing. So there's the orange, and then there's the red. Okay. This one will then, this one will lead us to 41.7, or I'm going to go ahead and put 42 degrees with respect to the normal outside, so that would give us then the complementary to 42 degrees is 48 degrees, so let me make sure that I get to 48 degrees, so just like that. Okay. Alright, and now we're going to go with the 40 degree angle and start to get a little bit. So notice how the effect starts to get a little bit more pronounced here. So as we go 40 degrees, then let's take our ruler and put it 50 degrees from the horizontal or 40 degrees from the vertical. Would bring a ray that looks like this at 40 degrees from the vertical. What angle will that result in? If we run our calculation, that gives me 58.7 degrees, or we'll say 59 degrees here, so 59 degrees. Let's pull up our ruler and go to the complementary of 59. Remember, this time we're actually over on this other side over here, there is 0 degrees, here's 90 degrees, and we want the complementary to 59 degrees, or almost 60 degrees, which would be 31 degrees, right? Okay. Let's bring that back over here for later. That is, now you're really starting to see how it's bending as it gets to the surface of the water here. Make sure that you're calculating this along with me, because this is going to be very important that you understand your own calculator. Everybody's calculators are going to respond to this differently. We're about to hit something that's outside of reality. Okay, so if we run this through our calculator at, we should be calculating that the angle of exit, the exit angle, theta air, is going to be equal to the arc sine of index of refraction of water over index of refraction of air times the sine of, and in this case we're going to do 50 degrees, but I'm going to go ahead and write theta water here, and if you put that in, you should get some result that is going to be kind of nonsensical. So your calculator should give you something like error. My calculator actually gives me an imaginary number, which look for an I at the end of your, if you have like I think the Inspires do this. Some of the calculators will have an I at the end. Do not be fooled by that I. It's not a real number. It's an imaginary number. Or your calculator may just say, oh, I've got a problem. It might, catch on fire, blow up, or something like that. Not really, but it's gonna go. Basically, this is what your calculator is doing. Okay, so when that happens, no matter what your particular calculator says, this is what the actual feature is that's happening. So we're coming in at an angle of 50 degrees with respect to the normal, which is 40 degrees with respect to the horizontal. And then what occurs here is it cannot actually exit the water, so it reflects. And when it does, it follows the rule of total internal reflection. If we are 40 degrees with respect to the horizontal here, we are also going to be 40 degrees with respect to the horizontal here, or 50 degrees with respect to the normal will be 50 degrees with respect to the normal here, and this is what will happen to your ray. So this is an interesting effect and is actually pretty useful in lots of different aspects of how light behaves in everyday life. For instance, let's go to a different screen here. So for instance, fiber optic cables operate in this way. Okay, what I've drawn here is a fiber optic cable, and so you've all heard of fiber optic cables. You've perhaps seen some of the cool effects that come out of them. There is really a lot of cool effects that have to do with fiber optic cables, but let's address the function of them in particular. So as fiber optic cables operate, we get a ray of light inside one end of the fiber optic cable. We'll go ahead and put it in a simple fashion directly into the end of the fiber optic cable in a way that is perpendicular to the surface of the entry surface into the fiber optic cable. Okay, and what occurs here that you may notice is that we've got part of our fiber optic cable that is rather dense, and then the next part of it is less dense. And so, as you would imagine, going from a more dense region to a less dense region, you're going to get a refraction. So let's take our refraction in this bent cable to be, it doesn't have to be bent, it can actually be straight. As a matter of fact, it's better if it's not bent. But this shows the power of a fiber optic cable. We can take our normal to the surface here, and as you can see, the angle with respect to the normal here is quite large. So let's go ahead and put that angle, I'm going to put that in green so we don't confuse our rays with our angles. It's quite large. Now what we studied earlier in the video is that the total internal reflection demands that if you go from high density to low density at too great of an angle, then you're just going to get a reflection back in. And so we will then demand that this ray reflect right back in. I think it's something like that, right? So our ray reflects back in, and then the next time it hits an interface is right here. And then of course we would expect that same result. This, if it strikes right there, we would expect that same result, that it needs to reflect back in. And then the next encounter that it has with the surface is again going to be at a dense to less dense interface here. Let's draw our normal again, and we would expect it to be something like this. And because of that, then we would not get a refraction out, because it's way too shallow of an angle with respect to the surface, and way too wide of an angle then with respect to the normal, the same as it was here. Our angles are way too wide with respect to the normal, and so we would then get another reflection, a total internal reflection, and as you can see, the message, the light ray that is sent by fiber optic cable, even on a bent cable, happens to be pretty decently reflected all the way through the cable. So, and then if we manage to get a ray escape, let's say if this angle here is still not quite steep enough to prevent a total internal reflection, then you can still manage to get a very, 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 very sharp refraction. And then when that happens, you get to the next layer, and even if you failed to totally, so this is in the case that we did fail to totally internally reflect on one account, we would still be able to totally internally reflect on the next outside. And it's much easier to get rays of light to go from a less dense medium into a more dense medium than it is to get them to go from a more dense medium into a less dense medium, and so it has a tendency to capture the light and carry it through that core in the fiber optic, so we refer to it as the fiber optic core. Newer fiber optic cables do not have this stratified look to them, or this sort of like layered look to them, but in fact look a whole lot more like this, so they would look more like this, where they have a gradient of indices of refraction, so that if you had a ray of light that came in at some kind of angle, like let's say this angle, then as it approaches the middle, if it passes the middle, then the index of refraction gradually steers it back toward the middle, and then once it passes that middle mark again, it gradually steers back toward the middle again, and then gradually toward the middle again, and it keeps doing that until it gets to the other end of the cable, so that it transfers the data as smoothly as possible. Now, because you might have some rays of light that enter here and don't have nearly as much trouble getting to the other end, so that less time passed for this ray of light than for this one, we have something called a loss of coherence between rays of light that are in a fiber optic cable. So this means that we have to be, if we have a particular cable, then we go a certain distance and we lose coherence, and then we have to have a fiber optic sort of recoherence station every maybe kilometer or so. There's a lot of data that goes into, a lot of computer science that goes into reprocessing the signals every kilometer or so to make sure that the fiber optics the signals are cleaned up and then resent out on the next fiber optic bundle. So it's actually not the fiber optic cables that are expensive, it's actually this reprocessing technology that is expensive about creating fiber optic infrastructure. Now, another really cool thing about the total internal reflection is the concept of a mirage, which is a mirage, like, I mean, when you're totally dehydrated in a desert and you get a mirage, there's psychological elements that, you know, get real Bugs Bunny about that. But when you're just driving on a road, a simple mirage is completely an optical effect. So sometimes you'll be driving on the road, you see like what looks like little puddles of oil or water, and what's really occurring here, it looks like a reflection on the road, but that's not actually what's occurring. What's actually occurring is a refraction that's very similar to what's occurring in the case of a fiber optic cable. So it's like total internal reflection, but it's a gradual effect. And so let's look at that. So essentially, what occurs in the case of a hot road on a hot summer day is that you have varying temperatures where the road is extremely hot and the region above it is is a little bit cooler and a little bit cooler and a little bit cooler. And I'm going to flip this so that you can see it instead of in terms of temperature, in terms of air density. And the reason for this is because when we have a hot road and the hot air expands, so that means the density is less of this air, and as it gets cooler, as it goes up, then we get, so for cooler air at the top here, we get more dense air. So in terms of the index of refraction, then we would have a ray of light that, now I've discretized this so that it's not as difficult to see, so we'll actually have some interfaces here between different temperatures and different densities of air. So we might, and of course this is a really exaggerated effect. In fact, the rays of light have to be coming in something like this, but I don't have enough space to show that. So we're going to show an exaggerated effect where a ray of light comes in like this, and then as it hits this boundary, this interface, from a greater index of refraction to a lesser index of refraction, then it has this very overly pronounced effect here, where it is going to bend away from the normal. Remember, our normal is going to be at this 90-degree angle here, and is going to be given by this sort of dotted line here. And then we have a new normal that occurs down here. And so this new angle here, rather than being that angle, is actually going to be bent again away from the normal. And as you can see, it's definitely going to gradually cause this sort of increase in altitude of the angle, right? Now, eventually what's going to happen is the perturbations are going to lead to, if it were exactly like this, then it would lead to this being exactly along the surface, but these little ripple effects cause this to essentially cause a total internal reflection at some point. So, and then that's going to cause this to go back up again, and then when we get to the next layer, again, this is a very exaggerated effect, right? But plenty of air, plenty of heat, and plenty of line distance for you to see it. The effect causes you to see what looks like, essentially it's going to look like this when you're driving on the road. You get a ray of light that comes in from a car, like a headlight or something like that, at something like 7 degrees, so it's a reasonable angle. And when you're far enough away, then you see a ray of light coming in like this, and what actually occurred there is this sort of gradual bending effect that occurs. So that ray of light comes in like this, is gradually bent upward, and it looks just like it would if it were to reflect. So this is some of the behaviors that come from total internal reflection. If you check your book, you can see that another important total internal reflection effect is the droplets in the sky. rainbows. So this completes this week's videos. I encourage you to check out more material on this, ask me questions as necessary, and hopefully I'll see you in the morning sessions.